So these two questions, uh, I searched a little and now I understand what they mean when they say the EMF. They mean the induced EMF, right? And by induced EMF, I don't mean the EMF that is induced because of the actual acceleration that the electrons need to be in that motion. No, I mean the EMF, like what is apparently the force that's, I mean, the extra force that's pushing the electrons, developed because of the magnetic field. All right, only the magnetic field. That's the induced EMF that they are talking about. So yeah, according to that, let's say we solve this question first of all. Right. So they are saying that this is a midpoint C over there. Okay, there's a midpoint C, and we want to find the potential difference between C and B. So what do we know? The EMF, that, like, okay, what's the field, the induced field because of the magnetic field at this point? Well, it's moving with velocity v, it's at distance r, so you can say that v equal to omega r. So v times b, that will be the field, right? And so our EMF should just be integration of this field dot dr. Our field is what? B times v, which is b omega r, and then dr. These should be vectors, right? But you get it that right now r can also be thought of as just a quantity, scalar, right? And yeah, so it's gonna be what? And I should say from C to B. So that will be b omega r squared by 2, and goes from what to what? At C, the thing is L by 2, and then it goes to L, right? So b omega upon 2, and then r squared should be L squared minus L squared by 4, right? So 3/4, so 3/8 b omega L squared. Let's see if that's in the options. Yes, it is. Right, cool. And similarly, we want to solve for this one. So over here, once again, it's going to be the same thing, integration of, yeah, like b omega, and this time I'll just use vectors. So r vector dot dr vector. Yeah, that's better. Right, so you want to integrate this thing throughout this path. Cool. uh yeah, how do we do this thing? Well, integrating it throughout this path, this thing is like just constant, so pull that out, right? B omega. And now r dot dr, that's like a mathematical thing completely. And yeah, if we are gonna say like integrate this thing, what is this thing? It's the area. It's the area after all. Isn't that right? Well, no, it's kind of more complicated than that because it's dot, not cross in this case. So what does dot mean? Hmm. I don't know. Well, one thing we know is that this thing for like a loop, for example, well, that should be zero because it's only dependent on this r vector. So if it's going from the same thing to the same thing, I believe it should be zero, right? Like, yeah, like if this is r, then you can have this r, and then that is our dr, that dot, well, initially it's zero, and then it goes till here, it's all positive, but then after that it's all negative with the same magnitude, so it will cancel. Yeah, so that looks like a logical thing to say, okay, cool, r dot dr, well, the integration of that thing for a closed loop is going to be zero. So it only depends on what the final and the initial and final position, I guess. Yeah, right. I mean, why are we even talking about this thing? This integration, it should just be r squared by 2. Isn't that right? Wait a second. R dot dr. Yeah, well, this integration r vector dot dr vector, you know what I'm going to say? It's like integration of magnitude of r dot d magnitude of r. Yeah, that's what I'm gonna say, because if you are like over here, and then your dr vector is pointing in some direction, the thing is that the component that's pointing in that direction, that's what you will take, right? Your R is now in that, yeah, R is now having magnitude like this, sure, but the actual thing that you got is this thing. Yeah, that makes sense, I guess. So is this thing same as like dr, which would be what? Okay, this is getting complicated. Just you know what? Yeah, let's do it like this. Instead of writing like that kind of vector, I will write it like this: xyz dot dx dy dz. Right? So now it's gonna be what, like three different integrals, and what's the integral of x dx? Now this is a much better question, isn't that right? So you're going from this point to some point like that. What's the integration of x dx? That's all they're asking. Well, x, yes, that's nice. So it doesn't matter what path you take, it's only like initial and final. That's all that's gonna matter. Cool. That means it really is r squared by 2. So I should just say delta r squared by 2. Right, so that will always be our EMF in this case. Right, cool. So let's think about it. What's our, okay, PW by 2, what's the final r squared? Well, this thing, which is L squared plus L squared, okay, minus the initial r squared, which is 0. Yeah, so this is gone. So yeah, that's the thing. B omega, okay, that's the thing. Cool. Okay, next we have figure shows a uniform magnetic field B confined to a cylindrical volume, and is increasing at constant rate. Okay, the instantaneous acceleration experienced by an electron placed at P. So it's a cylindrical volume, uh, uniform magnetic field P increasing at constant rate, instantaneous acceleration experienced by the electron placed at P. All right, fine. This one is acceleration. Well, this thing is not exactly moving, right? Yeah, if this electron is not moving, why should it experience anything? It should just be zero, I think. A cylindrical volume, but it's not exactly a conductor, isn't it? Yeah, that's right. And this guy is not moving. It should just be zero. What's even this question? I know it will try to resist this flux from changing and everything. But like, this is, yeah. Or is there something different about this? Wait a second. No. Uh, oh god, this is complicated. I know it's not moving, but then there's induced electric fields, which would make it move, I suppose. Right? So, like, if you got this uh, conductor and there's magnetic field changing, I mean, the flux is changing through this loop, you get the current. But then you can say, okay, fine. There's magnetic field that's changing, but why should the electrons care? They are not moving, they're at rest, right? Yeah, you could say that. Uh, of course. But then really the electrons are not at rest over there, so this is not a good example. On average, they are at rest, but then there's that velocity that matters. Mm-hmm. Right, so all we know is that there is some kind of field that's induced. Is this even correct to say that? Should this thing just start to move out of nowhere? I don't get it. Why should that happen? Like, yeah, why? If I can believe that this will have a current in it, then it's okay to believe that this will also start moving just by itself. Isn't that right? Yeah, I think so. And then we can use the radial symmetry and say, okay, fine, I'm gonna use Faraday's law for this loop over there. right? And it says that integration EDL, that's like what? That's the change in flux upon, okay, negative of course, change in time. Yeah, sure. And where's the field pointing in in this case? So this is going to be some non-zero quantity, and field should be radially symmetric, right? So whatever angle the field makes with, yeah, like uh, field making some angle with that. Okay, okay, fine. I oh god, should it make some kind of angle with it? And then actually should be dot vector like that. We can only talk about the tangential components like that. Okay, cool. You can talk about the tangential components and stuff. Hey, wait. Okay, this could be different altogether. Like change in flux, which is surface integral of the magnetic field. Dot dl. Well, that thing is more or less like the curl. I mean, the surface integral of the curl. So the actual thing was that the curl of the field, the electric field, that must have been equal to negative of the magnetic field. Isn't that right? So can't we just use that in this case, right? Where this is changing? Yeah, curl of it. I mean, okay, if there's magnetic field, what's telling you that there won't be an electric field over there? It can be, after all, these are connected. So it's alright to assume that. Wow, this is complicated. Okay, whatever, I'm just gonna use this. I'm just gonna use Faraday's law and say that okay, this is like E tangential times the length, which is 2 pi r, that's equal to negative d flux upon dt. Well, yeah. Oh shit, what's the area? Pi r squared, right? Negative pi r squared, and then d flux, d magnetic field upon dt. Cool, that's our E tangential. In that case, like E tangential equal to, well, this goes over there, pi gets cancelled, r gets cancelled, negative 1 by 2 dp by dt. That's complicated. Alright, fine. So that's our tangential electric field. What about the normal one? Like, should there be any normal electric field? There might be. After all, if there is like something like that, it will still make this law work. Yeah. Oh god. Instantaneous acceleration experienced by electron placed at p, so you got some kind of field over there, right? So the tangential field is like this, and what's it? It's changing, it's increasing, right? It's increasing at a constant rate. So it's, yeah, if it's increasing, and this thing is positive, and we know in what direction, sure. And then our uh, area vector is going down, that means our path goes like this, so our tangential field, that's going to be in that direction. But it's negative, so actually it's in this direction, so it's gonna go to the left. Wait, no, it's an electron, not a proton, so then it's gonna that direction. Fine, so it's to the right, though I doubt it, because it could also have an upward component, so why not that? I don't know. Okay, move on. A triangular wire frame, each side equal to 2 meters, is placed in a region of time variant magnetic field having, so given dv by dt, triangular wire frame, sides are given, the magnetic field is perpendicular to plane of, okay, the base of triangle has resistance 1. other two sides have resistance 2, the magnitude of the potential difference between the points A and B will be potential difference. Once again, which EMF are we talking about over here? What do we mean by, I mean, in a non-conservative field, you don't actually have anything like a potential difference. There's no potential in the first place. So it must mean the potential difference of the electric. Yeah, like just the conservative field. Okay. So you got EMFs over there because of the magnetic field. And huh. All we know is just the Faraday's law, right? We know what the area is and stuff, like cool, I get it. Hmm. Two sides of the potential difference between points A and B. This is like, it's not just the EMF, is it? Is it? The integration EDL in Faraday's law, that's like, yeah, the actual EMF over there. The actual thing that what electron really feels, not just components of it. So we are not talking about that thing because they said potential difference, so it must mean just the field because of the charges that got induced, right? Uh-huh. Okay, this is no good. Charges that got induced. You know though. Fine. I'm just, I don't know how to solve that. I'm just gonna say, okay, that integration EDL, that's our potential difference. All, yeah, but once again, that's stupid because integration of ADL will be different if you go like that or like that, right? Yeah, I mean, okay, it's going inside, so we will say that our path is like this around the loop while using the Faraday's law. So according to that, uh, field should be pointing in what, that direction, right? Yeah, in this direction for this guy, and then like this. So integration EDL for this path is negative while for this path is positive. That's bad. That's not good. What? I don't get it. What do you mean a potential difference? It's not conservative in the first place. And then there could be like, okay, fine, charges got developed. Yeah. Ah, come on. Okay, whatever. Okay, fine. What's the area? It's just square root 3 by 4 times the side square. Call this L square. That times the magnetic field change in that, of course, like square root 3 Tesla. What is L first of all? Side 2 meters. So that times 2 square times square root 3. That's our EMF. You can say that. Right, cool. Which is okay, that upon the total resistance, which is 2 plus 2 plus 1, that's 5. That's our current, and that times the which EMF are we talking about, this one or that one, or like what the heck. I'm just gonna say, okay, this one, that looks good. So that thing is just 1. Yeah, then this should be the answer. So it's gonna, what is, it's gonna be 3, that gets cancelled, 3 by 5, which is 0.6. All right, cool. This is probably wrong because I don't know what they mean by the EMF in this, the potential difference in this case. EMF we know. Okay, in the adjoining circuit, initially the switch S is open. All right. The switch S is closed at equal to 0 difference between the maximum and minimum current that can flow in the circuit. Maximum and minimum current that can flow in the circuit. Alright. So we need to write equations for this. So you got 10 volts over there. This is an inductor over there. What the heck? Right. If we try to use Faraday's law, it will be just stupid. So you instead you have to assume that it's just a component that creates a potential difference. Yeah. Across this thing, there's some kind of potential difference, like some kind of opposition. You can say that. And we know how much that is. It's just L di by dt. That's the potential difference across it. I'm gonna assume that. And then you got whatever's the current in going in that direction, like say I1. So plus 10I1, that should be equal to 10I2, I think. Yeah, that's right. Okay, that's cool. And what else do you want? Oh, this all this potential difference stuff, that should be equal to 10 volts. That's good. So you know that I2 is just 1, right? And you got this thing. Oh, so I1 changes accordingly. What do we want? The maximum and minimum current that can flow in the circuit, the difference in that. So this is constant, so ignore this thing and just think about this. Think about I1. That's all we need to find. So using that equation, you got L di1 upon 10 minus 10 I1 equal to dt. So you got L by 10 natural log, actually negative natural log of 1 minus I1. uh yeah, actually should be change of that and stuff. So I1 2 upon 1 minus I1 1, that's better, equal to t. Let's talk about the initial condition. That initially I1 was, well, what, 0, right? Because inductors resist current initially, so it was 0. So it was just 1 in that case, right? The denominator was just 1. So you got this equation, right? So you, what's the L? It's 0.1, so it's going to be 1 upon 100 over there. Yeah, that's good. So natural log of 1 minus I1, that's equal to 100t. Alright, and what do we want to find? Maximum and minimum current. When will this be max? Of course, it's just 1. That's the maximum that it can be. Yeah, so like, cool. That's gonna be 1. I'm pretty sure about this thing. Maximum current is 1, minimum is 0 for this wire. And then of course this doesn't make any difference. So it's gonna be 1 amps. Nothing can be concluded. Well, it can be concluded because at t equal to infinity, we know that this inductor just behaves like a wire. So there's only current 1 ampere in this wire, and then initially it just tries to resist, so there's 0 current, right? The rate of time constant in charging and discharging in the circuit shown in the figure. Rate of time constant in charging and discharging in the circuit. Okay, shown in the figure. Fine, it's pretty much the same as the previous question. Right, so ignore this thing, like, yeah, let's talk about this one. So you only got V equal to I times 2R, so 2IR plus L di by dt. Cool. So from that you have di, okay, L di upon V minus 2IR equal to dt, right? So L natural log, we know initially it's just going to be that, so upon V and then V minus 2IR. Oh, it's negative. Yeah, equal to dt. So putting that over there, you get like v minus 2ir upon v, that is equal to e power negative, yeah, of course, 1 by l times t, so t by l. Time constant? That's weird. Oh, that's how it works. I don't get it though. Uh, no, something's just wrong. Things wrong about this. That's it's like legit time. LDI by all that stuff. Oh yeah, of course. There's this extra stuff over there. You have to talk about that as well. So it's not just negative. It's like negative. Uh, this thing. That definitely okay, like negative 2r. That's better. That's better. So 2r l. This is our time constant. Tau 2r l. Right. That's cool. So the ratio of time constant in charging and discharging. Oh, right. So now we also want to figure out the discharging. But there's no potential difference. There's no like, okay, cool. There you go. Now it's charged. Right. Once there's that current, the maximum current going through it. And then we just stop this. Right. Discharging is different. There's this maximum current going through it. What's the maximum current, by the way? It's just V upon 2R, right? All right, cool. Sorry. So it's V upon 2R current going through it, and then it's decreasing. How is it decreasing? Can you write the equation for this? Is gonna be that loop, right? So initially the current is that, so it will go like this. Isn't that right? So the potential drops, that will be LDI by dt, right? LDI by dt plus 2RI plus RI equal to 0, of course, because there's no external flux change over there. That makes sense. Yeah, so you can just say that di by dt, LDI by dt equal to negative 3RI, right? Cool. And that means that L natural log of I up, say I final upon I initial, that's gonna be negative 3 R T upon L. Is that right? Or did I mess up something? No, that looks right. Okay, that looks fine. So you just got what? I final upon I initial equal to E. Yeah, this is gone. Equal to E power negative 3 R T by L. Or you can say, oh, we know what I initial is. I initial is what was that once again? Yeah, it was like V upon 2R. Okay, cool. That's all right. So you got this thing. That's how that works. The thing is that L upon 3R, that's our tau in this case, right? Over there it was tau equal to 2RL. Yeah, here it's different altogether. Something's not right. Something's just not right. Did I do that correctly? No, maybe I didn't. Oh no. Oh shit. Yeah, it was. Oh, I was going to integrate this thing, not differentiate. It should be upon 2R over there. That makes sense. Right. So it should be not that, and it should instead be negative 2R upon L. So tau should be L upon 2r, right? That's the thing. One has L upon 2r, one has L upon 3r. So that's in charging and that's in discharging. So charging you got 1 by 2, discharging you got 1 by 3, which is 3 is to 2. Good, that's the ratio. All right. I think we have got a lot and it's maybe time to check all of this. Let's check this. It was last time we left at 20, I think. Yeah, whatever. All right. 21. C, B, cool. BAC, BAC, cool. BDC, DBA, okay, DBD, sorry. DBD, 35th, BAC, oh wait, no, 36th, it should be A. Okay, fine, and then it's C. And 38th, B. 39A, we didn't do it yet. Okay, we didn't do it yet. Fine, so I'll just stop here for now. See you in the next video.